Let's calculate this. Do the following way. Yeah. So commutator. Lx x commutator. Okay, what is Lx? Lx is ypz minus zpy. So ypz minus zpy. It's z, should be z. Sorry. And we should commute it with x using this equation. So we write down that ypz x minus zpy x. Then we can use this relationship to expand this commutator. However, we see that x commutes both with pz and y, and here x commutes both with z and y, and so no matter what no matter no matter what commutator you will take, they will be 0. So that gives us 0 because x commutes with each multiplier and each term of this of the left-hand side commutator. So what about the next Lx Lx y equals to y pz minus zpy y. Okay, y pz y minus zpy y. So it's the same thing. Y commutes both with y and pz. That is so this commutator equals to 0. However, y commutes with z, but do not commute with y. So as z commutes with y, we can just drop it here. Actually, z commutes both with y and py. That means that is why. Or actually, we can use this relationship. We can rewrite it. Can write it in the following way: BC commutating with A equals to equals to BA C plus BCA. Yeah. So what I have done, I just changed the sign, reversed the product in reverse the commutator and reverse this one and this one. So it's just a reversion. That is why we can check that it equals to minus. So either we can just minus BA. BA is ZY and C and PY minus or plus Z PY Y. So you see that this commutator equals to 0 because Z and Y are just multiplication, 0. And this this commutator, we know that commutator px x px equals to ih equals to ih up. And the same thing holds for ypy. That is means that px equals to minus ih using this property of the commutator and the symmetricity, and so we get plus izh. And the last thing, I forgot that Lx should be there is h bar. Sorry. There is h bar behind Lx, so Lx equals to y pz minus zpy divided by h bar, and that means I should divide it here by h bar, h bar, h bar, h bar, h bar, and I get what iz. So, and using the same relationships, you can get all 9 commutators. Note that here we could have used the explicit form of the momentum operators, let's say, to substitute it by derivatives, and we would get the same results. But this approach is much more easier because you don't need, you just use commutator algebra. So the same relationships holds for momentum, and the last thing is this relationship. Not the last, but last basic commutator is that commutator, if you commute different projections of the angular momentum on different axes, it will give you the projection on the third axis. So the commutator, here's commutator Lx Ly equals to I Lz. However, yet you know the two equal operators, let's say Lz, they always commute because they're equal. They can be permuted. So I'll give you another 5 minutes. Try to prove this relationship using all this Lx Ly commutator. Let's write decompose Lx so Lx equals to over here. Lx equals to 1 over h bar y pz minus z py. Here Ly. You see, we do not need to express Ly because we already have expressions for commutator between Ly and Py and Z and all these terms. This is why we do not need to express Ly in terms coordinate and momentum to calculate this commutator. This calculation is much easier than if we decompose Ly. So 1 over h y pz Ly minus z py Ly 1 over h. So here I wrote down the specific case when either B or C commute with A. In that case, if B commute with A, you you can just move B in front of this commutator and get this term. And if C commutes with A, you just move C here behind, in front of, not in front, but after commutator, and get this term. So be careful, the order of operator is very important. You cannot mess them up. So y commutes with ly. That means that we can leave it here. And py commutes with ly, because we know that if, let's take this example, if I equals y and j equals y, or somebody likes I equals 2, j equals 2, because 1 is x coordinate, 2 is z coordinate, and 3 is, sorry, z is y. So we've proven that ly equals to 0, because in that case you have to write I equal to, g equal to, then epsilon 2 to k should be 0, because it has two equal indices. That's why we can y commutes with ly. We can put it here and write down 1 over h y pz ly minus, let's do that, py, oh sorry, py should go here, z ly py. Okay, zly. Let's check what is zly. We know that lyz equals to ix. That is why if we reverse them, so zly will equal to minus ix. It's minus ix. What about pz? Pz, we have to write down this equation. No problem. So for this case, this relation will read L ly, so L2, pz is P3, L2 P3 equals to I, so j equals to 2, epsilon j equals to 2, k equals to 3, and we know that the only non-zero term will be here if we put L equal to 1. So L equal 1, P1. That means that Ly commuting with Pz will equal to I Px, and we have to calculate this. So let's move. Let's count. Let's count the. Let's count the switches. So epsilon 2, 3, 1 equals to minus epsilon 2, 1, 3 equals to plus epsilon 1, 2, 3 equals to plus 1. So times 1. So Ly Pz equals to Ipx. That means that Pz Ly equals to minus Ipx. Minus Ipx. So 1 over h. Oh no, that's okay. 1 over h minus I y px plus, because it's minus here and minus here, ix py. So we can move I further, and we get I over h xpy minus ypx. However, let's look on the definition. We see that xpy minus ypz is lz. Lz multiplied by h. That's why xpy, it should be y here. xpy minus ypx divided by h bar equals to lz, so we get ilz. So let's check. Yeah, it's ilz. And the same way we can prove other correlated relationships. So another important operator is L squared, which we remember that L is a vector, so it has 3 projections. And L squared is given by the sum of squared projections. Squared projections Lx squared plus Ly squared plus Lz squared. You can easily okay, we have a little time. Let's check the following commutator. That's L squared, commutator of L squared with Lx equals to L equals to 0. Using this commutator. I'm sorry, one more thing. Here we have introduced the large letter L, which stands for the sum of angular momentum of all particles. So this L is the angular momentum of single particle. But if we work with the system of the particles, the total angular momentum equals to the sum of angular momentum of these particles. And people, they usually use the large letter L that denotes the angular momentum of the whole system. And later we will work with the large value, large letter L, denoting the whole, the total angular momentum. It holds the same correlated relationships, but it is more useful to work in L because later, because people usually work with system of the particles. So try to prove this correlated relationship. So let's calculate the this commutator. First of all, I have written the simplified version of this equation. If C equals to B, we can write down the following relationship. It's up if C equal to B, we can write the following. So let's do it fast. This Lx squared plus Ly squared plus Lz squared, we commute them with Lx. So Lx squared with Lx plus Ly squared Lx plus Lz squared Lx. It's Lx. Commutator of Lx with Lx squared equals to 0 because it's this same operator. Then we have to calculate this commutator ly squared with lx. So let's use this relationship, or we can rewrite these relationships vice versa. B squared a equals to ba. So I just switched these operators, b plus b ba. Actually, you can write it. You can write in that way, equals to b commutator a b equals to ba. It's commutator of ba with b, because you see that's the one operator, that's the second operator, so it's mutual commutator. What about ly lx? Ly lx, ly squared lx, if b equals to y, ly, and a is lx, so we can write the following: b is ly, commutator ly with lx, we commute with ly one more time. So ly lx, we know that ly lx equals to minus I lz, minus I lz, because here it is written lx ly. Note that L small and L large um, is governed by the same relationships, commutator relationships. So ly lx, no, it's lx ly equals to minus ly lx minus lz. So it is minus I lz ly. Then minus I lz ly, lz is y, is given by minus I lx, minus I lx yeah, equals to minus lx. So this commutator equals to minus lx. So, and then for this commutator we can do the very same thing. Okay, let's do that. Lz ly. I do it a bit faster. Lz lz squared lx lz equals to lz lx equals to I ly. I ly lz and equal to I ly lz equals to I lx. Minus lx. So this commutator ly lz and y, yeah, ly lx, lz lx, yeah, and then ly lz minus lx. So the sum of this term is 2lx, but there should be some misprint, some mistake, because they should have opposite sides. Give me a second. Unfortunately, I do not see the where is the misprint, where the mistake, and I will recover it after the lecture. So somewhere we missed the sign, and there should be different signs, and we should get here 0. In the same way, you can prove these relationships, and so what we have found. We have found that commutator of any, let's say, Lx, Ly equals to Lz, ILz, and that is not 0. But commutator L squared Lx equals to 0. So what we see that the commutator of two different angular momentum equals to do not equal to 0. And only the commutator of angular momentum projection with itself equals to 0, but it is trivial. And but commutator of squared angular momentum with projection of the angular momentum equals to 0. What does it mean? You remember that from the physical side, from physical point of view, if two operators commute with each other, then you can measure these quantities together or simultaneously. If not, you cannot measure. And that means that these relationships, they say that you cannot measure two different projections of the angular momentum, or projections of the angular momentum to different, let's say, x, y. You cannot both measure Lx, and Ly. But what you can measure Lx, projection of the angular momentum on Lx, or Lz, or Ly, and square of the angular momentum. What do we mean by square? What is the square of the vector? The square of the vector is its length. So we can measure the length, the square of the angular momentum, and its projection. So in classical mechanics, we could have measured all three projections and the square, which equals to the sum of all three projections. But in quantum mechanics, we cannot measure these three projections. We can measure only one projection, and the square of the projection of the angular momentum, the square of the angular momentum. So that is a very important thing, and that give me 5 minutes. I want you to explain on the experiment, from the experimental setup. You remember the Stern and Gerlach experiment when you put some particle through the inhomogeneous magnetic field, and it goes up or down depending on its projections of the angle, its projection or its angular momentum projection on the z-axis. Let's say Lz. So we get plus 1 or -1. It can be 1 or anything else, but for simplicity I will put it +1. So then if we take this branch and measure the and put it put these particles, move this particle through the instrument measuring the same z projection of the angular momentum, the 100% of these particles, so let's say it's 50% and 50%, will go to the 100%, go to the +1, and -1, 0% will go to the -1, obviously, because we know the z projection. However, if we measure x projection, so if we have the particle with a definite value of projection of angular momentum on z-axis, and we measure the projection of its projection on x-axis, we get 50% going to plus x and 50% going to -1. Okay, still here we know that we can measure one more time x axis, and 100% will go to +1 and 0% will go to -1, because we know the x projection. But there's the question, do we know that this particle, so how we choose this particle? We know that this particle has z projection equal to +1. Then we took the particles with positive projection of angular momentum on z-axis, put it through the x tool, and have taken only those particles that had projections that had positive projection of the angular momentum on x-axis. So here we should have Lx equals to +1, Lz equals to +1 So if we measure this particle, we get 100% the z projection, 100% +1, 0% -1. That what would be in classical mechanics, but we do not work in classical mechanics, we're in quantum mechanics, and we found that Lx and Lz do not commute with each other, and so they cannot be measured together. And that means that when you measure the x projection of the angular momentum, you erase information about these measurements and this and erase information about the z projection of the angular momentum. And that means that if you measure this if you measure the angular momentum one more time, you measure the z projection, you wouldn't get 100%, you would get 50% +1 and 50% -1. That is how things are done. And this experiment can be the setup of this experiment is very easy, because you can rotate or you can rotate your instruments, so you can put the particles through the vertically oriented tool. Then you can take the same tool and rotate it 90 degrees, and therefore it will measure the projection of the z-axis angular momentum of another axis. So actually, yeah, that's it. So you cannot know all three, even you cannot know just two projections of the angular momentum on some two different axes. However, as we saw, you can know both projection of angular momentum on some axis, and the square and the absolute value of the angular momentum. Okay, let's take a break and find out. We will find out the eigenvalues and eigenstate. Let's find out the eigenvalues of the L squared operator. So we have found that the eigenvalues of Lz is the integer numbers, or integer numbers times, if we are speaking not about z, about not the dimensional Lz by not dimensionless Lz by dimensional one. The projection of the angular momentum on z-axis is quantized, and it equals to h times some integer. M equals to 0, plus minus 1, plus minus 2, etc. However, you should understand that we're speaking about the z. We're speaking about the z-axis, but in reality, you can name any axis as z. And why we're speaking about z-axis but not and the projection of the angular momentum on any axis x, y, or z in any axis would be integer. But why we're speaking only about z? Because mathematically it is easier to calculate the projection of mathematically the expression for Lz operator is most simple, the over the phi, and experimentally you just can say you can name each any direction as a direction. So that's why the it do not the generality of our equations still hold. So now we want to find the eigenvalues of L squared operator. Here's the equation for this L squared operator. But please do not be afraid. One way to calculate the eigenvalues for L squared to write down some function y depending on theta, phi, and calculate this let's say L. Okay, I'll name it L. Not L. It's over okay, A times y theta phi. So one can solve this equation and use boundary conditions due to periodicity of the function with respect to phi. However, this equation is pretty not so simple. It is partial differential equation. Its solution is can be difficult. So I will show you a more elegant, more beautiful way to calculate the eigenvalues of L squared. However, before that, we have to introduce some auxiliary operators, L plus and L minus, which is defined in the following way. Note that Lx is the operator of the physical quantity. That means that Lx is the Hermitian operator. So it means that Lx Hermitially conjugated equals to Lx. However, L plus and L minus are not Hermitian operator, because if we try to conjugate L plus, we will get Lx conjugated plus I conjugated, which equals to I complexly conjugated times Ly conjugated. So Lx conjugated and Y conjugated equals to Lx and Y, but I conjugated equals to minus I. Means Lx minus I Ly. So you see that L plus conjugated gives L minus, and vice versa, L minus conjugated equals to L plus, equals to L plus. So it's mutually conjugated, Hermitially conjugated operators, but they are not Hermitian. So there is no observable state corresponding to that, to these operators. One more time, we need to calculate the commutator. I will give you a couple of minutes, and then we'll do it myself. But these commutators are much more easier. So try to calculate this one. I'll put these commutators in the homework, but they're very simple actually. So let's do that. It's really simple. So commutator L plus Ly equals to commutator Lx plus ILy with Lx minus ILy. So we can expand these commutators. Lx, this one. So let's take this, and this, and this. Okay, so Lx minus I Lx Ly plus I Ly Lx and plus no, minus I squared Ly. So Lx equal to 0 because it's equal operators. This equals to 0. Lx Ly, we remember that Lx Ly equals to I Lz, and Ly Lx correspondingly equals to minus I Lz. So we get minus I squared Lz minus I squared Lz equals to 2 Lz. So here we get corresponding using the same technique we can calculate these commutators, and so that's what we need. Okay, we'll skip this one. Yeah. We want to calculate the eigenvalues of we want to calculate the eigenvalues of L squared operator, this one. First of all, if our system has some absolute has known value of f of L squared, it means that it has L squared, and we know, let's say we know that Lz, which equals to mh, some integer, times h bar. This integer, this m, let's say this system has some L squared value. You understand that Lz squared should be less or equal to L squared, because the square of the projection, if we take let's take two-dimensional system for simplicity, sorry. You understand, if you have projection LZ, LZ, this projection cannot be larger than the absolute value of the vector. It can be smaller, but it cannot be larger than the absolute value of the vector. Actually, in classical physics, you understand that if you have some, there is a maximal if you know the absolute value of your vector, your angular momentum, which is L squared. L squared is the square of absolute value. Then, and you know the projection, then the maximal projection of the vector on the z-axis would be square root of L squared, which is L, which is what comes from classical mechanics. However, let's look closer on this state. If we have the LZ equals to this LH, where L is the maximal projection of angular momentum on z-axis, that is L. That is L. In classical mechanics, that is the maximal projection. In classical mechanics, the absolute value should be L2, because you just rotate this vector towards that axis, align with the z-axis, find that the absolute value of the vector coincides with the maximal projection, its maximal projection on the z-axis. However, if you look on the state when you have LZ equals to L times H and L squared equals to L squared, you easily find out that Lx equals to 0 and Lz equals to and Ly equals to 0. So in that state, you can measure all three projections, Lz, Lx, and Ly. Lx and Ly are 0 because you have your maximal projection on the z-axis. You aligned the angular momentum with z-axis. However, you know that you cannot measure three projections of the angular momentum on different axes, and that means that L squared could not be equal to the square of the maximal projection of angular momentum. Okay, so we denote by M the projection of the angular momentum on the z-axis. So I denoted by I showed it by these points. It's 1, 2, 3, 4, -1, -2, -3, and we denote by L small, the largest possible projection of the angular momentum on z-axis. In that case, L equals to 4. Okay, so let's do some math. If you act, and let's denote by psi m a state in which the system has a definite projection on the z-axis equal to mh bar. So psi m corresponds to one. This one is psi 1, this is psi minus 1, this is psi minus 2. So that's the states corresponding to definite projection of the angular momentum on z-axis. That means that psi m is eigenfunction of Lz. So it holds the following relationship. Let's act by operator L plus on this on the both sides of this equation. We get the following equation. Okay. However, let's use this commutator relationship. Let's expand it. Lz L plus minus L plus Lz equals to L plus. That means that L plus Lz equals to minus L plus Lz equals to L plus minus Lz L plus. So L plus Lz equals to Lz L plus Lz L plus minus Lz. Am I right or not? So Lz L plus minus L plus Lz equals to L plus. So L plus Lz equals to Lz L plus minus minus L plus. Yeah. So that's what we get from this commutator. Okay, let's substitute this. Yeah, sorry. So LZL plus acting on psi m, vice versa. Sorry for a bit mess. LZL plus equals to L plus L plus Lz. We can get from this equation. So let's look on this thing. LZL plus acting on psi m. We substitute LZL plus by L plus plus L plus Lz. Here it is from the commutator relationship, from which, this one. Then we introduce the psi m here, and we find out. Let's do it more. So this leads to L plus Lz psi m plus L plus psi m. However, Lz psi m equals to m times psi m, because psi m is the eigenfunction of the operator Lz. That is why we can write that it equals to L plus acting on m psi m plus L plus psi m, which is this parenthesis. And if we gather the terms, we simplify equation in the following way. So what we see is that the function, let us write down it one more time. Lz acting on L plus psi m gives us m plus 1 act L plus psi m. That means that this function L plus psi m is the eigenfunction of the Lz operator with eigenvalue m plus 1. That means that L plus psi m should be proportional to psi m plus 1. So, what L plus operator does? It increases the projection of the angular momentum by 1. And the same thing holds for L minus. L minus decreases the projection of the angular momentum by minus 1. So I hope it is clear. So that is our relationship. Let's take the state psi L, where I recall L is remind you L is the largest projection of the M. So M is less absolute value, less or equal than L. M cannot be larger than L by definition because L is largest. So psi L, and we act on psi L by operator L plus. So what we get? We get psi L plus 1. However, we know that there is no such state with angular momentum that is larger than the maximal projection. So the psi L plus 1, there couldn't be such state. That means that L plus 1, psi L plus 1 equals to 0. So we depict it here. I hope it is clear that there could not be such state with the projection of the angular momentum that is larger than largest value. That means the phrase couldn't be such state in quantum mechanics means that the function, the wave function, the function of the state equals to 0. So L plus acting on psi L equals to 0. In the same way, we understand that L minus acting on psi minus L corresponds to negative projection, to this one, to this projection, equals some constant times psi minus L minus 1. But still we cannot, there is no states larger than the largest in the absolute value projection of angular momentum. That means that it's a 0 too. So that's very important. Then so let's take this equality and act by this equality by operator L minus. So we have L plus psi L equals to 0. So we can act L minus by L minus on this. Since it is 0, it should be still 0, because acting by a linear operator on the 0 function should give us 0, equals to 0. However, what is L minus acting? What is this? What is this product? Okay, let's calculate. We remember that L minus is Lx minus I Ly, and L plus is Lx plus I Ly. So we get Lx squared plus Ilx Ly minus Ly Lx and plus Ly squared plus Ly squared, because we multiply this operator and this operator. So let's look on this. What is written here? It is I times commutator Lx Ly. But we know that commutator Lx Ly is Lz. Lz. Oh, sorry, ILZ. Which means here we have minus I minus Lz. Minus because here's I, and I squared equals to minus 1. So what we have here is Lx squared plus Ly squared minus Lz. We can add L squared here and subtract it, plus Lz squared minus Lz squared. And we see that Lz squared plus Lx squared plus Ly squared equals to L squared minus Lz squared minus L minus Lz. So we found that L minus L plus equals to L squared minus Lz squared minus Lz. And we know that L minus L plus acting on psi L equals to 0. So we can write this equation. So let's simplify this equation. Okay. Here we will expand it. L squared L psi L minus Lz squared psi L minus Lz psi L equals Lz acting psi L. We know that psi L is eigenfunction of Lz. We know that Lz psi L equals to L times psi L. So, and Lz squared in the same way, Lz squared psi L equals to L squared psi L. So what we get is L squared psi L minus L squared psi L minus L psi L. Psi L, and all this equals to 0, which means that L squared psi L, here is L, equals to L times L plus 1, which is L squared plus L psi L. So we see that psi L is the eigenfunction of L squared, and its eigenvalue is L plus 1, or in other words, L squared plus L psi L. So yeah, that's it. Equal to L squared plus L. Why have we got this result? We see that in classical physics we expected to have L squared equals to L squared and nothing more. However, in quantum mechanics, we already discussed that if the L squared would be equal to L small squared, then if L squared equals to L squared, then Lz equals to L, Lx equals to 0, Ly equals to 0. That means that we if L squared would be if the square of the angular momentum equals to L squared, the square of the absolute value of the angular momentum on z-axis, then we would know all three projections of the angular momentum. However, it is impossible, and that is why L squared equals to L squared equals to its eigenvalues equals to L squared plus L. What does it mean? It means that if you are in the state with a maximal projection of L on z-axis, you still have some uncertainty in Lx and Ly, and this uncertainty contributes to the L squared, and this contributions equals to L. So that is why the L squared eigenvalue equals to L squared plus L due to these fundamental uncertainties in Lx and Ly projections of the angular momentum. Last thing I want to tell you here is that there is one state where you can measure all three projections on the angular momentum. Is the state there is one exception, and this exception is when Lx equals to 0, Ly equals to 0, and Lz equals to 0. If all angular momentum of all projections of angular momentum equal to 0, then they can be measured. So there can be a state in which all three angular momentum equal to 0. However, it cannot there cannot be state where you can measure one angular projection of angular momentum equals some m, and this one equals to 0, this one equals to 0. There cannot be such state. Only the state with all three equals to 0. So either you have all three projections equal to 0, or you know only one projection of the angular momentum. Okay. So that's all what I wanted to tell you about the angular momentum or the particle. I will skip this part for now, and as the last part of this lecture, I want to speak a little bit about the particle spin. We talked about the angular momentum, and classically speaking, the angular momentum can be we can imagine angular momentum in two ways. One way, when one particle moving around some center, and this case is the case, let's say, hydrogen atom. where the electron moves around the positive nucleus, positive proton, and this electron has an angular momentum, non-zero angular momentum. It can have non-zero angular momentum. However, the other way classical mechanics to obtain an angular momentum is to take the particle, the solid particle, and to rotate this particle around its center. So to take a ball and to rotate it. Here I want to speak about this kind of angular momentum. So the spin is the angle of momentum of the particle, which corresponds to the inner rotation of this particle. However, every estimation show that there is an experimental evidence of the spin. It have done 100 years ago, and people sure that there can be the angular momentum of single particle, which is not rotating around something, but it looks like it is some inner rotation of this particle, like I have drawn here, like inner rotation of the ball around itself. However, all calculations or estimations show that the measured angular momentum cannot be represented as the inner rotation of the particle, because particles in quantum mechanics are point-like particles. They do not have dimensions, because the wave function gives us the probability to find out the particle at some point, but it do not give us the information about the size of this particle. And in quantum mechanics, in elementary particle physics, the particle do not have the sizes. They can have so-called scattering size, when it's the effective size of the particle that you can measure by scattering one scattering one particle over some other particle. So you scatter and you can measure the effective size, but this effective size depends on the charge of this particle and all other things. And that means that spin, it doesn't have the classical doesn't have a classical analog. The spin is a pure quantum mechanical quantity. There is no such quantity as spin in classical mechanics. And as I told you, the most often and most common value of if we take an electron, there are two possible projections of the spin on the z-axis, which is 1/2, +1/2, and -1/2 for electron. And in spin physics, so the wave function of the particle should depend not only on the coordinate, 3 coordinate, but on the spin. However, we know that the spin is corresponds to angular momentum of the particle, inner angular momentum, and we know that the projection of the angular momentum on the z-axis or any other axis is discrete. It can take only discrete set of numbers. And that means that this fourth coordinate, fourth sigma, can have only discrete numbers. And that is why the wave function can be displayed, can be written down as a vector. The first vector, each component of the vector depends on the coordinate x, y, z. But this component of the vector, it gives us the probability of the particle to have spin sigma 1. This component gives us the probability of the particle to be in the state with spin equal to sigma 2, and etc. Actually, so, and each component depends on each component depends on coordinates. And so I said that this component gives us a probability. However, the probability would be given by the integral of this component. So probability to have sigma, the spin equals to sigma 1, is given by the integral over every coordinate psi x, y, z, sigma 1 dx dv over whole volume. So that gives us, I'm sorry, should be squared. That would give us the probability to have spin, and that to have spin equal to sigma 1. And all probabilities should sum up to 1. That means that the sum by sigma should equal to 1. And that is the normalization condition. Working with the spin means that we should we should represent our wave functions as vectors, and usually the vector we work in so-called the z-axis representation, and the vector 1, 0 corresponds to the particle that have spin plus 1/2, and the vector 0, 1 corresponds to the particle having spin minus 1/2. You see that the difference between 1/2 and minus 1/2 is 1. So the angular momentum projection still changes only by the integer number. However, however, it is not. It differs. However, before we showed that sorry, we showed that the angular momentum LZ can have only integer values. But if we introduce the conception of the spin, and the experiments show that it is so, the spin can have half integer projections. And actually, that's all. You cannot have spin 1/4 or 1/3 or anything else. You can have spin only either half integer and 1/2 h, or integer spin. And the particle that have integer spin, so the spin can have, okay, let's take the particle with spin 1. The projection of this spin can be either 1 or 0 or -1. If we take the particle with spin 1/2, its projection would be -1/2 and plus 1/2 and -1/2, because the angular momentum should change only by the integer number, not by half number. We can take the spin particle with spin 3/2, and then its projection, this projection of the spin on the z-axis or any axis, can be plus 3/2, plus 1/2, -1/2, and -3/2. So if the particle have a half integer spin, all its projection should be half integer. And if particle has integer spin, all its projection should be integer. The particle having integer spin is called bosons. So that's boson. And this particle is called fermions. And these particles have different nature. Actually, all our matter is made of fermions. The electrons are fermions, the protons, electrons are fermions, protons are fermions, neutrons are fermions. So our atoms are made of fermions. However, and what is the bosons? The bosons represent the elemental. If we are speaking about elementary particle, the bosons represent the particle that is responsible for interaction. Let's say photons are bosons. The photons are responsible for electromagnetic interactions. What bosons do we know? There is gluons, which is responsible for so-called strong interactions. This interaction by which quarks and nucleons in the nuclei interact with each other. And also there is a W and Z bosons that is responsible for so-called weak interaction, but it is not a theme of our lecture. So what you probably know it, but recall that there is fermions that have a half integer spin and the bosons that have integer spins. So if we're working with fermions, it is easy to the plus 1/2 projection we denoted by the up arrow minus spin equals to plus 1/2, spin equals to minus 1/2. And we represent the spin plus 1/2 by the state, we denote it by psi with upper arrow, and the vector which corresponds to this state is 1, 0. And the vector which corresponds to spin down is 0, 1, because and the arbitrary the state uh, uh, the superposition of the state A psi up plus B psi down can be denoted as AB, and A squared will give us the probability to find out the particle in the spin up, and B squared gives us probability to find out the particle spin down. Then, as we work with vectors, then our operators, as we have discussed, can be represented as matrices. Well, I will skip. And the projection of the spin on the z-axis is given by such matrix. Projection of the spin on the y-axis, the operator of the projection, is given by this matrix, and X is this matrix. These matrices, this one, and this one, are called Pauli matrices, and is denoted as sigma z, sigma y, and sigma x. Do you have 5 or 10 minutes more? Can I take your 5 or 10 minutes time? Okay, let's move. So let's take the operator LZ, and act on the psi on the spin up state. So what we obtain? 1 0 0 minus 1 acting on 1 0. So what we get? 1. Let's take h halved. We get 1 here and 0 here times h halved. So, which means h halved psi. So, psi up is the eigenfunction of Lz with eigenvalue h halved. We can do the same thing. Lz psi down equals to h halved 1 0 0 minus 1 times 0 1 equals to minus, so we get here, what we get here is 0, and what we get here minus 1 h halved, which equals to minus h halved 1 0 equals to minus h halved psi down. So psi down is the eigenvalue of the Lz, the eigenfunction or eigenvector with eigenvalue minus h halved. So let's try another thing. Let's take Lx. Let's act by Lx on on psi up. So what we get? H halved 0 1 1 0 acting on 1 0. What we get? Here we get 0, and here we get 1. H halved equals to h halved psi down. So we see that psi down, Lx acting on psi up, gives us h halved psi down. That means that psi up is not the eigenfunction, eigenvector of operator Lx. And Actually, the Pauli matrices, they satisfy the same. Give me a second. The same relationships as the angular momentum. Well, this is obvious because angular momentum is given by in matrix representation. It gives the you can check that Lx times Ly, Lx and y commutator, Lx Ly gives us minus Iz. So sigma x commutator sigma x sigma y gives us 2 sigma z. So up to some multiplier, they are quite the same. We can check it actually. Let's check it. Sigma y sigma z. Okay, let's check the commutator sigma y sigma z. Sigma not sigma z, sigma y. Sigma x is just 0 1 1 0. So sigma, let's calculate sigma x sigma y minus sigma y sigma x. Sigma x is 0 1 1 0. Sigma y is 0 minus I 0. Let's check. Yeah. Minus vice versa. 0 minus y minus I 0, acting on 0 1 1 0. So let's multiply this matrix. What we get? This row on this column gets I. This row on this column gives 0. This row on this column gives 0. This row on this column gives us minus I. Okay. So this one, this row on this column gives us minus I. This row on this column gives us 0, 0, and this row, this column 0. This row, this column is I minus. So we just subtract one matrix from another, and we get 2I is 0 0 minus 2I equal to 2I 1 0 0 minus 1. That is sigma z matrix. So we get 2I sigma z. So we have proven this correlator relationship. And other relationships can be proven in the same way. So that's all for today. So we have spoken about the angular momentum. We have shown yesterday and today that projection of the angular momentum on each axis can be only integer number. So if we measure the projection of the angular momentum on some axis, we always will get a discrete spectrum. We found that we showed that apart the projection of we showed that you cannot measure projection of the angular momentum on both axes. You can measure the projection of the angular momentum only on one axis, and measuring the projection of the angular momentum on one axis erases the information of the projection on the angular momentum on another axis. And then we show that actually there are two two combinations of the angular momentum that we can measure. We can measure projection Lz, and we can measure L squared, which equals to Lx squared plus Ly squared plus Lz squared. We can measure both of these values, and we show that eigenvalue of L squared equals to L times L plus 1. Meaning that even if you have the maximal projection of the angular momentum on some axis, let's say Z, the uncertainty in Lx and Ly projections will give you additional L to this. And then I've told you a little bit about the spin, and that the spin can be either integer or half integer. Half integer spin correspond half integer spin the fermions. The particle that have half integer spin is called fermions, and elementary particles having the fermions. Elementary particles fermions corresponds to the particles of the matter, and the bosons correspond to particles of the that is involved in exchange of interactions. And we showed that for 1/2 spin we represent our wave function as a vector, two-component vector, and the operator is the matrices, and the matrices is given by Pauli matrices, which is written down, and they satisfy the same relationship as the angular momentum, and we have proven one of them. One more little thing I want to say. I have to say that the atom, the combined particle, the particle that is combined of two fermions, can be boson. Let's say if we have the helium-4 atom, a nucleus which is composed of two neutrons and two protons. The total spin of this, let's say if neutrons have spin 1/2, 1/2, 1/2, 1/2, 1/2, the total spin is integer, let's say 2, if all projections is plus. And the combined particles of the matter can have integer spin, and can be a bosons. So that's all. I'm sorry for a bit of a rush in the end. And the next lecture, I wouldn't use so much of the math. We will talk more about the quantum optics experiments and more deeper understanding of quantum mechanics. So that's all. If you have any questions, please feel free to ask. Thank you.